And whether you can, do I have to hold this all the time? I guess. Um, it's like, it almost seems like that TV show, Come On Down, what was that? Let's make a deal, but we're not making a deal. All right. Oh, I can't. Anyway, the title of my talk is sort of Data Science and Analytics at the University of Maryland. And, well, okay, what I did was I prepared a poster. It's a one-page flyer. I'll try to bring them for the demo if you're interested at the poster session, but it shows some of the work that we've done. At the upper left is a document retrieval system based on locations. So you give locations by specifying on the map, and it gives you documents that have, related that location in them. The other example there is we have a system for reading news with maps, and we'll give you a little demo of that. We also have, looking at photos, and you can see in the lower corner there, it says photo stand. You see everything better than I do here. And there's a cover of Communications ACM, which had an article written by our group and made the cover and a video, which if you click on my home page, you'll see a little triangle that shows it to you of it working. In the upper right is a book that I've written. I've written 3 books on spatial representations. That's sort of my key area, is representing locations and algorithms to do things. Now, that's that in there. And the other interesting thing is the map with all the colors in it. And what it does, it represents the average driving distance to work for all residents of a pixels region. And the amazing thing about this work is that we're computing road distance, not Euclidean distance. You go to Google and they'll sell you a product called Distance Matrix, and all it can handle is 25 by 25 is the most you can do, and they're Euclidean as well. We do is real road distance. We can handle 30,000 by 30,000 matrices. These are OD matrices called origin destination. The most that FedEx or UPS and so on can handle is 125 by 125, which is why a delivery truck carries 125 packages, because they can be optimized. With our work, you can do 30,000 by 30,000, which means you can optimize a warehouse. So you can figure out what everywhere goes, and you don't have to drive and use gas. So, and the interesting thing about this work is that we do it in order n space. The matrix itself is order n squared. It uses something called the theory of well-separated pairs, and Professor Ramani is a Weld expert on this area as well. And this stuff is pretty neat. So let's go on. So here's just an example, shortest path and distance computation. Go ahead. You can see this is an example of Dijkstra's algorithm, which will explore 80% of the vertices. You see what we do, we only explore the vertices on the shortest path. Go ahead. And this is just an example that, if you go to Google and try to find the 10 nearest restaurants to Newark Airport that are Moroccan, it gives them to you as if you're swimming. And we're not swimming across the Hudson. Next. And here just shows you the different orders. I gave these slides, so if you're interested in my work, you can look at them afterwards. And you can see a little explanation. Go ahead. Next. What we do is, our work is based on pre-computing the shortest paths. Go ahead. And what the advantage, go ahead. You see here, you see A, B. These are groups of vertices, and what happens is you partition the map into these pairs of vertex sets, and it turns out that if I give you 2 vertices, 2 locations, I find they're containing either A and B or whatever that contains them, and there's order n of these pairs, okay? And that's why it's order n space. And this is the same example. Go ahead. And these are things you can do with it. All right, next. Okay, the other main part of my work is a map query interface. And basically, you point a location, and the interpretation of the precision is equivalent to what we call a spatial synonym. Now, what we are looking at is textual specification of location. See, we've all been brainwashed to use geometry, but geometry, do you really know that you're at lat long 55.666, comma 59.837? Of course not. And nobody knows that. So when you communicate where you are to other people, you're much more likely to use words or text. Okay, I say I'm in Connecticut and L, or I'm across from Barney's, I don't know, Barney's something in New York, isn't there? Howard's in New York, or Barney's Beanery, or what is it? Or I don't. Clothing, yeah, okay. But there used to be something with beans also in some book I read. All right. Anyway, so the point is we're used to these textual specifications, and the nice thing about text is that it behaves like a polymorphic type. What does that mean? If I give you, let's say Los Angeles, it's great because in some cases all you're looking for Los Angeles is a point. In other cases you're looking for a region or boundary. You don't have to do that. That's really sort of inheritance and object-oriented systems. All right, now the drawback, the drawback of using text is ambiguity. You see the word London is a person or a place. Okay, moreover, if it's a place, there's like 3,000 of them. Which one is it? Of course, it says London, UK. It's not hard, but we're looking for the general problem. Go ahead, Romani. So here's just an example of AT&T, telling everybody that they can handle this type of work. I found these ads in the Travel and Leisure magazine when I flew to Australia. And this is my research. Sort of interesting. You see this in a magazine for public consumption. Next. So these are just examples of why location is important. If I tell you, what, the score was 28-0 in football, well, it would probably not be rugby, depending on where it's played. Next. You get temperature, I tell you, it's 28 degrees in Cancun. Well, if it's Cancun, Mexico, it's 28 centigrade. If it's, Cancun, not Cancun, but say, what location am I there? Just Mexico, right. So if it's Mexico, in New York, 28 degrees is Fahrenheit, and it's cold. Okay. All right, next. Next, there's no more? Yeah. Shows there's 33 different Plymouths in the U.S. Next. Here's an example of a map of the U.S. with ambiguous locations. A ton of them. Next. All right, now let's look at this. John, I'm going to show you how some of that works. Yeah. What we have is the system for reading news with maps is done, works on a laptop and a big screen, but we also have it working in a small device in your hand, and just thought you'd like to see it. All right. One thing, what I want to stress is we do our research bottom up. So my students and my group, we generally work on a problem by implementing things and then finding the solutions to problems that come along. My philosophy in doing research is that you should never ask your professor for a problem, because if you go to your professor and ask for a problem, what do they give you? Something they couldn't do. You need to do something you can do, okay? And that's hard. Now, if you're working on a system or building something, you're already halfway there because you started already. You run into a problem, and since others have not run into it, they don't know it, and so you don't have to worry. Students are always looking behind them. Who else is doing this? And one of my students has this problem, and so really, it's best. I think so. It doesn't mean that every professor will do this, but are we ever going to get there? Or yeah. All right. Okay. So here, are we? Can you see what I'm doing? Yeah. So here you could see these are all, clusters or articles by location. Now, what I'm doing here is I'm doing an SQL query that retrieves from the database everything in this window. And this is all done in real time in my office. So let's go to World. Let's go to Washington. But you see how I'm navigating with my fingers. Okay. So have we gone to Washington? Oh, what happens here? We were too quick. Okay. Where are we here? Here, I think Washington here. All right, you see Washington, D.C. I have one headline in a lot of clusters. All of these here headlines are from different clusters. So I pick one here. Then I get this something about the U.S. deficit. If I click on here, it'll actually give you the news story and show you what is happening there. See this Daily Chronicle. It turns out there's a video there, but you see how you can really read this. This is all on a small device, and you see here if I pick images, these are all related images to that topic. We also get videos. Now you can actually see them. And so what we're doing here, which is fascinating, is we're doing image similarity by the words. You understand what I'm saying? It's unsupervised learning, and you're given these words. If you're not doing it by color or texture or these type of features, just every article has a certain feature vector. It's a 1,000-dimensional feature vector based on the words. So you're finding image similarity by the words associated with them. It's pretty neat. I think I better stop. They're killing me. But if you're interested more, I'll have everything with me at the lunch at the poster thing, and you can see more and also the video. My apologies.